Hello, and welcome to Uber. My name is Isaac. I'm on the H3 steering committee. It's my pleasure to welcome you to Uber. I'd like to thank our hosts, and so say hi to your closest Uber person. If you want to want to learn more about the H3 community, which has brought us all here to learn about hexagons on the globe and all the cool things we can do with them, and continue the connections, please visit our website, h3go.org. There's also a Slack that is pretty active with people posting about what they're doing, announcements, events like this, things like that. That's all posted on the Slack. It's also not too much stuff getting posted there, so I really encourage joining that. QR code to join that is in the bottom there, and that'll be up on the screen again later. Another announcement, my company Fused is going to have a H3 conference coming up hopefully in the summertime. It'll probably be in New York. Information about that's not fully ready yet, but that'll get posted on that Slack as well. If you want to learn more about it, come find myself or Linda, who also helped organize this evening, and we'd be happy to tell you more. It's now my pleasure to move us into the talks this evening. After each talk, we'll have time for maybe a couple of questions. If we don't get to your question, don't worry, we'll have more time for that after the end of all the talks. Now I'm going to welcome AJ Friend. AJ is on the steering committee for H3 as well, very active contributor, former Uber data scientist. He's going to be talking about making cells to Polygon much, much faster. So please join me in welcoming AJ.
Well, I'll let you go first.
Hi, I'm Pradnya Goyal, and I'm a recruiter here at Uber. So if anyone is interested in opportunities at Uber, please reach out to me. I do have this QR code here. I'm going to leave it here. So if you're interested, please scan it, and then we'll have your information. Thank you.
Thanks.
Hi, everybody. So I should just be able to share my screen now. Is that right? Okay, cool. I'm sharing, but there it is. Great. All right, thanks everybody. Hi, my name's AJ. Can I advance? There we go. Like Isaac said, I'm on the H3 steering committee. I spent a lot of time with H3 and H3 Pi. And how I got into this, I was previously an applied scientist on Uber Eats real-time pricing. So what I'm going to talk about is, since I'm going first, a little bit of an intro to H3, and then I want to get to something I've been spending time on recently of developing a new function to translate cells to polygons, so H3 cells to polygons, and making that really fast. And to do that, because we're transferring to polygons, I'm going to also spend some time explaining what a spherical polygon is. And so the payoff here is that we're fixing some bugs. We're enabling sort of globe-spanning polygons, which are often hard to do in geospatial. And I have at least one example that's 200 times faster on pretty large inputs. So that's nice. And if people are curious or just want to go through the slides themselves, these are online already at that H3 cells to polygon -talk link. Somebody's taking a photo, so I'll give you a minute. Cool. Like a high-level theme. So if there's a theme to this talk and H3 in general, it's that there's benefits to discretizing continuous data. So H3 does that for geospatial data. And in general, that's useful for analysis, decision-making, visualization, data sharing, and the other talks today will go into some of those things. This talk is focused on, like I said, this one function for one of these, sort of the reverse of discretization, where you have discrete data in H3 cells, and you want to transform it back to continuous space, so back to polygons. We're focusing on this algorithm that does it. The original one, like I said, had some bugs. I'll get into that. That was because it wasn't using this discretization principle, but that was at the time the only way we could do it. We've since added some new objects to the H3 library, directed edges, and so we can sort of revisit this algorithm with that tool available and get some benefits. So high level, what is H3? We're discretizing the globe into hexagon and a few pentagon cells to enable easy geospatial data analysis. We aren't just cells, not just cells like these hexes here. We can also describe with the library edges along the sides of cells or vertices between cells. And all that boils down to a nice, unique, hashable 64-bit index like that. And of course, you can find more about that on the website. The H3 cells are organized into resolutions, depending on what data granularity you're dealing with or are interested in dealing with. At Uber, for example, 9 or 10 is pretty common because that's about the size of a city block. And these cells are related by parent-child hierarchies, which we'll talk about a little bit later. So I like this. I wanted this to exist, but it didn't. But just a quick zoom down of this is the highest level resolution in H3. There are 122 cells across the globe. And then I can zoom down to the next resolution, the next one down at 3, and then zooming in around resolution 7, a few hexes cover Manhattan. You can get down a few now at resolution 9, cover Central Park. Get down to Columbus Circle. The finest resolution, resolution 15, is about a meter squared, so that's taxi cab for scale. Using H3, we have lots of bindings, so you can use H3 pretty much anywhere you want in lots of different languages and lots of different databases. The core library is written in C. Data translation and discretization. You can do a lot with H3, but first, usually what you need to do is get your data into H3. So your data might start in some continuous format like GeoJSON, WKT, or shapefile. You want to transform that into the H3 system, typically into H3 cells, and then you do your work in H3 on the H3 grid. And then once you're done, you might want to transform back to a continuous data format. So to do that data translation, we have, I guess, 4 main functions that I'd say people use most of the time. So if you have data, if your data is point data, locations maybe, pickups, we can transform lat longs to cells, the cells we saw previously, and those cells you can transform back to lat longs to get the boundary or the center of the cell. You might not have point data, you might have polygon data, which I'll also give an example of, where you want to transform polygons to cells, and then also the reverse. So just for context of this talk is, of these 4, focusing on just that last step. So what does that translation look like? So this is the New York City taxicab data set. This is like data in 2010, while they still had lat longs available in the data set, which they got rid of later. So if we have a table like this, these lat longs are continuous, maybe some of these are 0 here. These functions are available in, I think this is DuckDB that I'm using, where we might take those lat longs, pick a resolution, and use an H3 function to transform it to a discrete cell ID, and we can do operations like here I'm doing a group by and counting the number of pickups in that month in New York City and this specific H3 cell. So what does that look like? So here's that data. That's why I needed to switch to my thing. So we have all this point data around here. If I do that transformation, then we'll get something like this. So this is at resolution 9. So you can sort of see some structures here. You see Manhattan, the airports, but maybe this is a bit too coarse for you. If you want to switch, you can switch to a different resolution. You're going to see different structures. So at resolution 12, you can really make out like city blocks and things like that. Or if you want to zoom in on JFK, you actually see sort of the pickup locations and where those taper off by distance. It's kind of nice. And just a slide for if we're back at resolution 9, you can always translate those cells back to their centers if you want raw lat long values. But this is now going to be snapped to the H3 grid. That was point data. So this is just giving you, what about polygon data? So here's, because we're looking at New York, here's New York again. This is probably from some Python library that has the boundaries of the New York City boroughs, the 5 boroughs, to represent those 5 boroughs, because there are lots of little islands. It's 106 polygons, 76,000 vertices. Maybe you don't want to deal with all that complexity, and so you want to discretize. So now you have 1,000 cells if you translate that to resolution 8 H3 cells. If you do your analysis, maybe you want to translate this back. And so you can take those cells and translate it back to polygons. So this will be 14 polygons, about 1,000 vertices, 900 vertices. And this is the operation that we're going to talk about today, is making this fast. When you have lots of polygons or lots of cells, you want to get back to that polygon outline. How do we do that bug-free for global polygons and super fast? So what's this new algorithm? What I just said, we have cells here. These are fun globes. And we want to take these cells and translate that to these spherical polygons, which have some orientation that we'll talk about. Why? For the reasons I mentioned, we'd had some bug reports that the original algorithm was having bugs with some examples, and that was coming from the fact that we weren't using discretization. We were representing edges and boundaries with lat-long points. And so we were doing floating point comparisons that always don't match up, and so we were getting some bad outputs. The algorithm couldn't emit global polygons, and it could be slow for large regions, or at least in comparison to what I'm going to show today. So instead of that sort of flat-long floating point representation, what if we use this new H3 directed edge object, and does that give us some wins? So I have to tell you sort of what we're trying to translate to, which is sort of continuous spherical polygons. And these are fun. These are trickier than Cartesian polygons than planar polygons. The simplest version is just a loop of lat-long points that defines an outer ring, and we'll talk about holes for those polygons. And these are oriented, so there's a direction on this edge. So it's like this point, this point, this point, and this point. And then I think you guys can see, there's an arrow, there's a direction on these. And GeoJSON, that would just be a list of those tuples. GeoJSON usually does long lat order, if I'm right, but it's a detail that doesn't matter much. Like I said, these are directed edges. These are geodesic arcs, so the shortest great circle distance between those points on the globe. So if I have points, so I've defined a fence with points, but which side of the fence is inside? So for a planar object, that makes sense. For spherical objects, it's not so clear. We need a convention to say, well, I've defined this fence, but inside or outside is one or the other. The way we do that is with, I guess the convention that we use is the right-hand rule. So if you're walking along the edge of the polygon, the right-hand rule says that the inside is to your left. I'm sorry that that's the opposite of what you would expect, but that's what the right-hand rule is. We can't change it. But that left hand is the inside is a good way to remember what it is. It's sort of, another way to say it is that loops are counterclockwise, but that doesn't always work out, or it's not obvious, so the right-hand rule is a more obvious way to do it, or more reliable at least. Because I can have that same fence, but if I switch the direction of the edges, then it defines, via the right-hand rule, the opposite side. So for this is everything except that on the globe, is what we're representing there, with that same polygon, but a reversed order. So would you call that counterclockwise still? It's still a valid polygon. That's still following the counterclockwise rule. It doesn't look like it, and that's why I defer to the right-hand rule is a better way to think of that. And this is the kind of global polygon that, we have this simple polygon, but it represents something bigger than a hemisphere. We want to output polygons like this with a new algorithm. Let's see, let's advance. So that was just a simple polygon with one region. We can also add holes to polygons by just putting another loop inside. The convention is that loops are oriented counterclockwise, but that follows just the same right-hand rule, that if you're walking along this internal edge, then the inside is going to be to your left. Those are single polygons. Multi-polygons are just lists of polygons. And so in this example, we have 3, 2 with no holes, 1 with 3 holes. On a sphere, the concept of one polygon being inside another doesn't make any sense, or it's not easy to define. So this is a flat list. There's no sense of one being nested in the other. So those are spherical polygons. Here's directed edges. So this is the new object in H3 that we can use that's going to power this new algorithm. Instead of pairs of lat long points to define this edge of a hex, we have this discrete object that has an integer ID that defines that same region. They're just defined by pairs of adjacent cells with an origin and destination. The origin, sort of similar to the right-hand rule, we're going to say that's to the left if you walk along the edge. And yeah, you can just flip the origin and destination cells, and that'll flip the direction of the boundary. Cool. In this interpretation, we're going to use these as a discrete representation of something that we can, at any point in time, switch back to continuous. We can always take the endpoints and convert that to lat long coordinates. And we'll do that when we're finally trying to translate this back to a polygon. So like I said, alternative to the continuous lat long pairs, this is a discrete version. It has a nice integer ID, and what's nice about that is we can hash these things in a way that you maybe can't hash a floating point or a pair of floating point numbers and compare it exactly. There's no floating point accuracy issues with these. I'm going to get a sip of water. Any questions so far? I'm going to just pause for a second. Cool. So what do we do with this? We have cells, we have this edge object, and we want to get to polygons. How do we start putting that together? Let's start with a base case. We're going to use sort of two important things, important transforms, where one transform can take a cell and we can transform that to the outer boundary edges. So all the edges, discrete edges around that cell. And then at any point I said we can take those edges and turn them to continuous vertices. So this is kind of the base case of this algorithm, this cells to polygon algorithm. I have one cell, how do I get one polygon? I can do it like this. If I can get those, if I can do that first step here, I have ordered boundary cells, I have the order, I can extract the lat long points, and I'll have a counterclockwise loop of lat long points, which is a valid polygon. Where I'm just assuming that we have sort of this primitive operation here that returns those edges in counterclockwise order. So this is going to be a primitive that we're going to use to, from this sort of base case, build up more complex polygons. And we'll sort of focus on these discrete objects, edges, because at any point we can always convert them to lat long vertices. So that's the base case. How do we start getting more complex? Well, if I have two cells, how do two cells interact? Well, if we put two cells next to each other, we have this symmetric pair. So these are two edges with the same origin and destination, just flipped. Maybe we can play with that concept. So the symmetric pair concept is going to be critical. So when plotting these, I'm going to plot lots of diagrams. When doing that, if this blue is the original outline, I can't plot both edges on the same line cleanly, so I'm just going to shrink it in and plot these edges like this. And then I'll drop the blue outline for these pictures. So what's the base core idea of this algorithm going to be? I get a bunch of H3 cells, I transform them to the set of edges, I look for these symmetric pairs, and I just cancel them out. If I find them, I take an edge, I look for its sort of reverse partner. If it exists, I can remove both. So when I do that, the only thing that's going to remain is the boundary of the polygon, or the boundary parts of the polygon. This is just a sketch. We'll fill in more details later. And if you know topology, this is something fancy like computing the boundary of a cell complex. So what does that look like for a disk of 7 cells? If we have 7 H3 cells here, I can transform them to their directed edge pairs, directed edges here, and then I can find, we have several symmetric pairs here. If you remove those, then all that remains is the exterior. And note, because we started with each cell being counterclockwise, by construction, this output is clockwise, or counterclockwise, which is what you want for a polygon. So that's a really nice property to have. What if we have something more complex with holes? So this is 28 cells, 3 holes. Do the same thing to directed edges. We're going to cancel all these out. It's beautiful. Like, it's just so nice. Like, you get the outside is counterclockwise. The 3 holes are clockwise, exactly as you need for the polygon sort of output that we're looking for. So what's missing? We have sets of boundary edges. These are just collections, but there's no order of these edges. We need to know sort of, I have a lat long, what comes next in the sequence to make these loops. And I haven't assigned polygons to, I haven't sort of organized these loops into polygons yet. So let's do some loop surgery. What do we want to do here? So we have the set of edges, and we want to take these collections of edges, and what we're going to start off with for each cell is a doubly linked loop of edges that's counterclockwise. And then as we're doing this pair cancellation, we're going to splice those loops together in a way that maintains the order of the loops that we sort of arrive at. So maybe I won't go into this in detail, but when we have 2 cells like this, we have maybe cell A and cell B with a sequence of edges A minus to A plus, B minus, B plus. We can, when we cancel this symmetric pair AB, we just need to do stitching so that A minus then goes to B, B plus, that goes around to B plus and A minus. When you do this, this can start merging cells from 2 loops into 1 loop, or it can split them. We'll look at some examples there. You can look at I think examples are probably easier than the actual code there. So what does it look for? Maybe we have 2 cells. We've already removed some edges from them. If we remove an edge, we can do the loop stitching to make that this is one valid loop. Those edges are ordered. We preserve the order, do the loop surgery, but we have this sort of degenerate edge sequence here. These edges sort of double back on themselves and don't actually sweep out any area. But that's okay. This is still a fine intermediate state, and loop surgery is going to work on these. And when you do that, you arrive at the same result. You have the boundary, but with the loop surgery, we've sort of we've maintained the doubly linked loop so that these are all in order. Any questions about that so far? Cool. And order doesn't matter. You can do this in any order. You can even have sort of this very bad degenerate state. That's fine. So if we have maybe rings with a hole, missing a cell in the middle, what does that look like? We translate to edges. We start removing edges. And now we have 1 loop, but it's sort of degenerate. And when we remove this last pair here, what's going to happen is we split that loop into 2, but we get this nice property that, again, this is counterclockwise. And then the hole in the center is clockwise. Everything we want to be true sort of falls out by construction. Like I said, this is a doubly linked list, so what you're doing under the hood is just pointer arithmetic. That is an exercise that nobody wants to do outside of college. But the details are there. So this is our algorithm again. It's the same, transform cells to edges. The only thing we've added is that when we do this cancellation of edge pairs, we just do the loop surgery on the way. Still not done. What are you missing? Loops to polygons. So we can construct the boundary edges. We can organize them into oriented loops. We can take those loops and get the lat long vertices. But which loops belong to which polygons? How many polygons do we have? And which of those loops are outer loops versus holes? So for one of those questions, we're going to track the connected components. So the idea is that we're going to initialize all these cells to be separate connected components. When we merge cells by canceling edges, that's going to merge connected components. And we just keep track of those connected components. You can do this efficiently with something called the union find algorithm, or it's like a disjoint set tracking algorithm that's well known. You can look at Wikipedia for the details. But after the cancellations, what state are you going to be in? All the loops that are in the same connected component, we're going to say belong to one polygon. So here's a colorful picture to demonstrate. So we've initialized it the same way as before, cells to edges. every cell starts off in its own connected component, which is given by a different color. If I remove this one edge over here, then we see what was two different colors merge into one connected component. This purple one down here is not going to change because it's not connected to anything, but let's keep going. So as we remove a few more edges, things start merging a little bit more. Some degenerate things here, even though everything here is merged together in gray, and keep going until you're done. You've gotten rid of all the edges. 3 connected components remain. This largest one has 4 loops. And the question is, so we've succeeded. We know we have 3 polygons. We've identified them. We've grouped these 4 loops, identified them as a polygon. We're not sure yet which one's the whole and which one's the outside. So we'll do that next. But just let you know, so this is the same algorithm. All we've done is update a bullet point here, that when we do that symmetric edge pair cancellation, we're just keeping track of the connected components. And I'll note, so far, everything we've done is pure graph theory, pure discrete stuff. We're not doing any floating point operations, which is nice. So, is it easy to tell which loop should be the outside for this one? Yeah, you just point it out. So this is a planar polygon. It's kind of small. This is easy. The trick is going to be to find a rule that works for these easy cases, but also generalizes to the sphere. Okay, here's another. This is one polygon, one outer loop and 3 holes. Which one's the outer loop? They're all clockwise. Any thoughts? That's yeah, maybe, yeah. Trick question. They're all so from a purely mathematical perspective, they're all valid loops. You can pick for any spherical polygon, even this one. You could pick this one to be the outer loop on a sphere and have this one be a hole, which is very weird, but that works. It works fine. So in this situation, it's somewhat arbitrary, but we need to pick one. But there is a way that sort of picks a natural choice or picks the right choice for these. So what are we going to do? So how do we come up with a rule that's going to pick this in sort of and match our intuition for these simple cases? And then whatever it does for weird spherical polygons is a tiebreaker that doesn't actually matter. So the solution is to follow the right-hand rule and figure out how much area those loops enclose. And ironically, we're going to take, or unexpectedly, we're going to take the outer loop to be the one that encloses the smallest area. Is that surprising? It should be surprising. Because, these holes seem smaller, but let's see what it looks like. This doesn't, let's see if I can do that. Yeah, if I do a refresh, and that renders better. There we go. So this is, we're taking this simple polygon. I'm plotting that on a sphere to highlight that it's a spherical polygon. And then for each of those 4 loops, I've highlighted in red the area enclosed by that loop if you follow the right-hand rule. So for each of these internal loops, those are clockwise, remember? So the area is to your left. So for this one, despite its humble appearance, it's enclosing most of the sphere. And that's true for all the holes because those holes are oriented that way. But the outer loop actually has the least area. So this gives it to you. That's the rule. So you compute the area for all the loops via the right-hand rule. The one that makes sense in the planar case is going to be the one with the smallest area. That's because holes encompass most of the sphere. So that's all you do. I'm not going to get into the math, but there's nice math that actually lets you compute the area for spherical polygons. It's somewhere, it ends up being a function, a value between 0 and 4 pi. In stradians, I think is called the unit. And then, the smallest area is going to be the outer loop. And this is the first time in the whole algorithm that we're using non-discrete math to compute this continuous area. Same algorithm, everything else is the same here, except we group the loops into polygons, and then we identify for each polygon which one's going to be the outer loop. And I'll just note that, so everything we've done so far is sort of what enables us to do global polygons. So things that are larger than a hemisphere, maybe crossing the anti-meridian or enclosing the poles. That's due to just everything being discrete sort of graph theory stuff that works on the globe. This area computation is selected so that it actually works on spherical polygons or spherical loops. And there's no need to like project your problem down to a planar subproblem, or if you do that, it's just not going to work. So, you know, there's no way to project this polygon down to a planar subproblem. That's going to tell you what it is. Or I like the twist. You can do the twist here. Is a cool one. So that's just a nightmare for how often you cross the anti-meridian. But these work fine with the algorithm I just outlined. So what do the benchmarks look like? So I've laid out the algorithm. I have this code up if anybody wants to play with it or criticize it. The old algorithm is the original algorithm. The new algorithm is the one we've been talking about, where we're using discrete directed edges. And it's 7% faster, or 7 times faster on this largest example. So the benchmark here is, I'm taking Colorado because it's well described as 4 points. So that's good for a benchmark. And I'm just translating that to the H3 cells at resolutions 3 to 9. So up to at resolution 9, that's about 2 million cells. The old algorithm takes about 14 seconds on my laptop, and the new one does it in 2 seconds, so 7 times. Pretty good. But I said 200 times, what happened to that? There's one last optimization we can do, and then we get it. So everything we did sort of laid the groundwork for this last step. Most of the work that we're doing is finding and canceling those symmetric edge pairs. What if we had a way to skip just big groups of those entirely? If we could, that'd speed things up. So the idea that we have is, if you know what H3 cell compaction is, we compact the cells and we initialize with just the boundary of the compacted cells, which I've been calling the Gosper Island. So let's talk about what that is. So H3, how many people know what H3 compaction is? A few, okay, good, everybody in the back. So H3, I said the cells are related by a hierarchy. So there are 7 children to a parent. If you have a collection of cells and you have all of a parent's 7 children cells, you can, instead of sort of having those 7 integers, you can replace it by the 1 integer that's the parent. And that gives you, 7 times smaller representation, at least for those cells. You can recurse this up the H3 hierarchy, so you can do it multiple times, and that can greatly reduce the number of cells and edges that you have to deal with. And for our algorithm for benchmarks, that we can compute this relatively quickly. So just to give you an example, we have 13 cells here, 7 form a complete set in blue, and 6 are an incomplete set. They're just missing this 1 cell. So if I were to compact this, I could replace those 7 with their parent here. Green's unchanged because it can't compact, but I get these like boundary issues that everybody complains about all the time. It's terrible. But I will argue that this naive cell geometry is misleading. This blue cell is the geometry of the parent resolution cell, but that's not what you actually care about. You're using that to represent the children. So you shouldn't plot the parent, you should plot the thing that it's representing, which is the actual children's geometry. So if you do this, those gaps go away. So you should just always be, if you see gaps, it's because you're looking at it wrong. You should be imagining this in your head, plot and interpret it this way. And you get no gaps, it overlaps. Did I say? So we'll call what this object here is sort of the first example of what I'll call a Gosper island. Like maybe technically a cell itself is a Gosper island, but we'll say that if we have this case where we have a parent representing children, maybe a couple resolutions down, the outline of those children, so the logical representation that that parent is serving, the outline or just set of directed edges we'll call that a Gosper island. I'm getting that term is a weird name. It's coming from the fact that there's a fractal object named Gosper Island that exists, that people named decades ago. and this is the same thing. And so what else do I want to say about this? So this could be, the lat long points making it up this island, or for us, what we're going to want to get in hand are the edges that make up this boundary. If we get that, then we get to skip all the internal edges in here. So for example, this is a Gaspar Island where the difference between the parent and the children is 1 resolution, 2, 3, 4, and you can sort of get the gist of why that's a fractal. So what does that look like for some real data? Here's Connecticut, has a nice aspect ratio for a slide. Better than Colorado is bad for the slide because it just looks like a block, but this is recognizable as a state, I think. So this is all the resolution 7 cells in Connecticut, 2,400 cells, 14,000 edges. If we do compaction and we plot it the nice way, those cells go down to 333, and we get 3.5x fewer edges. Where if I can figure out how to handle this, then I get to skip all these edges in these big cells here and some of the smaller cells. So that saves a lot of time. And this, how much faster is this? Well, it gets exponentially better with finer resolutions. And how it's going to work in your data just depends on how compactable your data is. So I won't have time to get into it, but what we need is a fast way to access just those boundary cells for any Gaspar island. I have an open PR for that. Somebody please take a look and we'll land it. And the nice thing about this is that this idea plugs directly into what we were doing previously. So this algorithm is basically unchanged. It's just the initialization that changes, where instead of the cells boundaries, sort of the base case of the Gaspar island, we compact the cells. Well, we first have to compact the input cells if they're not already compacted, and then we initialize with the connected components with the Gaspar island edges instead of the 6 cell edges. But everything else is the same. So how does that work out? This is the big win. So here I have those same Colorado examples. This is the old algorithm. This is the new algorithm, and then this is the new algorithm with the Gaspar optimization. So at 9, this is 200 times faster, just because we're skipping all those edges. You can get I'm counting in this time the time to compact the cells. So I'm assuming, to make it a fair comparison, I'm assuming everybody starts with a flat set of cells, and that's 200 times faster. But I think there are lots of applications where you can assume your data is already compacted. And if that's the case, you're in the happy place where it's then 400 times faster, which is pretty sweet. And I can make this ridiculous and be thousands of times faster if I just keep upping the resolution. But I think this is a good fair comparison. So this work is up. So most of the new algorithm is merged to the H3 repo, targeting a 4.5 release. We're on 4.4 right now. If you want to play with it early and sort of see how fast, ooh, what did I do? Don't click on that. If you want to play with it now, we have a pre-release of this on H3Py that you can pip install and play with. It's an alpha version, but you get that faster algorithm. You can see how much faster it is on your own data. The Gaspar Island iterator is an open PR, like I said, so we'll have to land that, and then we'll add that in, and we'll decide if that goes in 4.5 or not. And I think, just in terms of speeding up cells to multi-polygon, I think there's even more to do. I think there are other wins that we can look at that might get a few more factors of improvement. So summarizing, discretization is useful. H3 is one of the tools. You can use that for geospatial data. And that philosophy of discretizing stuff sort of paid off for this new algorithm, where we avoid floating point bugs for actually incorrect output. We're enabling those global polygons, and for these examples, it's a lot faster. Cool. Thank you. I can do a question or two if anybody has any. Yeah.
Does this discretization slow down anything else, like lat long to cell? Does it add any steps there?
I'd say lat long to cell is the discretization step.
Okay.
Yeah. I mean, I think maybe the comparison would be like, what was the old algorithm doing? And that was representing these edges as pairs of lat longs. And so like how fast can you do that versus take a discrete cell edge, compute the reverse, which is an operation, and then find if that reverse is in a hash set or not, hash map or not. So that is more work, but it is, I think I benchmarked it was about 12 times faster than just the time to do the initial step of a lat long to a cell. So it is a lot of work, but it's, yeah, it pays off, or it's a good trade-off. Any other?
This is, you said it's a lot faster for large polygons. What about for like very odd but broad shapes, like a route through a large area where you've got, you know, multiple cells, but not necessarily large area total? How does this perform in that case?
Yep, so the new algorithm is a little bit faster than the old one. So like this is without the Gosper optimization. So with the new algorithm, you should see speedups there. With the Gosper optimization, you're only going to see benefits when you compact your cells and you get these big, it's very compactable. Like there's a good compaction ratio. Because the speedup is directly proportional to like how many edges you can throw away with these things. Were there other questions? Yeah.
So the directed edges have their own ID.
Yep.
Does that contain information about its neighbors, or like what is packed in?
So I was saying the work to reverse an edge is kind of an expensive operation, but it's 12 times cheaper than a different lat long to cell operation. But it does require work. What's in the edge bit field it's just a cell. It's basically the representation of the origin cell, and then a couple of bits to say which of the edges of that cell this edge is representing.
Yep.
So if you have an edge, it's very cheap to get the origin, but it's expensive to compute the destination, or relatively expensive. The origin is free, basically. It's a bitmap.
I see. Okay.
Yep. All right, I think if there are any more questions, oh, sorry, Danny, yes.
Oh yeah, is there a method that you're using to do this visualization of the compacted cells that doesn't have holes?
Like, is there a method to like plot these Gosper islands? Like
Yes.
That would be, I guess, probably what you want is this PR. Like,
All right.
but you can do the cancellation yourself. But yeah, that's sort of the whole point, is that the trick is that I have a cheap way to do it that's maybe not obvious, because otherwise you have to do all that work yourself. Cool. That's it. If you have any more questions, I'll be around. I'd love to chat. All right, thank you, everybody. And now I think I'm handing over to Dimitri. Do you have a clicker somewhere? Or? Oh, it's right here. Well, that's the one with the laser. This one's just whichever one you want.
Let's do without laser so I don't kill anybody. Hello, my name is Dmitry. I'm in the GeoCore team at Uber. Our team does lots of things geofences related, like geofencing, geotriggering, and stuff like that. And we work heavily with H3 library, use it for indexing and also for clustering. And that's going to be my presentation, new approach based on the Leiden algorithm for hexagon clustering. So what I'm going to talk about is background on hexclustering, and then brief info on what's Leiden algorithm, and then how we construct the graph that Leiden is going to operate on, and then kind of clustering pipeline approach, and then a little bit details on like processing block inside the pipeline, and then some time for questions. So what's hex clustering is just kind of creating list of hexagon IDs that can be like algorithmically generated based on some metrics, or it can be just generated by drawing shapes and stuff like that. So it can be same resolution, it can be disjoint or joint, kind of different islands. when we store it, it can be compacted in compacted representation, which is save on space. And then for hex clustering, we have multiple implementations that we already did. Basically, it's greedy expansion based on either one metric or multiple metrics. And greedy expansion is just, it has a list of hex IDs, and it iterates over those hexagons, and just for each hexagon, it checks neighbors, can it be combined with this neighbor based on metric distance or not. And keeps doing those iterations until stop condition is reached. And it's either count of clusters or average size of the clusters. So this iterative approach takes very long time and not very optimal. And so recently we've been looking into different approaches for clustering. And another issue with this approach is that it works pretty well when the metrics are defined per hexes, but it doesn't work well when metrics are defined between hexes. And Leiden helps with that. So what is Leiden algorithm? It was developed pretty recently in 2019. It's used in network analysis for community detection of nodes that are more densely connected than other nodes. So benefits of it, it's improvement on Luvian algorithm. So benefits of it is it converges faster, it produces higher quality of communities. Sometimes Luvian would produce communities disjoint from the rest. Leiden doesn't have this disadvantage. And it has a parameter of resolution which allows you to control the output size. So is it going to be more smaller clusters or less bigger clusters? So low resolution, larger clusters, high resolution, smaller clusters. And we use Python for clustering, and so there are at least 2 open source Python implementation of this algorithm that we use one of them. So as I mentioned, Leiden works on graphs, and that's kind of the tricky part of the process. How do you construct graph from metrics that we have that will take into consideration metrics between different hexagons and also spatial component. And so what graph would be, the vertices would be just like hex IDs, and the metrics that we have between hexes, for instance, start and end, and number of trips that happen between those hexagons would be the weights of the edges. And so this is kind of natural edge. And to introduce a spatial component, we would, if hexes are connected, we would create an edge that would have small weight. And so when algorithm looks at it, it will tend to combine hexes that are spatially close. Okay, so how the clustering pipeline work, and this is kind of work in progress. So that's kind of going to describe the process, but we're still working on improving it. So first we do data fetching according to metrics that we have, and it will be in form of start hex, end hex, and number of trips or orders that happen between those hexes. And then we would construct a graph in the way that I represented before in the previous slide. So each pair like that would be created an edge, and also we will create those spatially related edges. and then we do kind of iterative approach. We would check, because we don't know for a given set of data what Leiden resolution would result in best clustering, we would consider all the resolutions from, let's say, 0 to 2, and do 200 iterations on the increments of 100 of following process. We would do kind of the graph constructed once, and then we would run Leiden with initial resolution, get initial clustering, and for example, this is one of the example of initial results. You can see that there is kind of lots of noise. There are bigger clusters, small clusters, and then so we need to do post-processing. What we would do, we would merge very small clusters into bigger clusters near them, For big clusters, we would run sub-Leiden. So we would take those clusters and portion of the graph that's related to the hexagons in this cluster, and we will run sub-Leiden with resolution 1, and it will be split. And then sometimes you can see some areas kind of protrude into other clusters. We would do some spatial smoothing and unassigned clusters if the area that we want to cluster, some hexes miss the metrics, so we would just assign them to the cluster that makes the most sense. And so how those kind of process blocks would work is this Leiden-based subsplit. So if you have a large cluster, you would just take some portion of that graph and run Leiden for it again, and it will translate into smaller clusters. For merging, in this example, you can see if you have 3 clusters, A, B, and C, and B is kind of small, and it's usually a parameter. Like for instance, 5 hexes would be too small, we want to merge it. We would try to combine it to neighboring clusters, like A and C, and whatever cluster improves metrics the most will be chosen. And then for edge smoothing, we do if a given hexagon has neighbors that belong to a different cluster, then we would merge it with a different cluster. And so this process will be continued iteratively. For each initial Leiden resolution, we would compute final metric, and then the maximum metric wins. And so, for instance, would the clustering result would be best for Leiden resolution of 1, and that will be the best. So this is example of result with all the edges smoothed. So from initial screenshot that I showed before, this would be the final clustering for a given city. So things that we continue improving is generalized metric combination. So now it works for 1 or 2 metrics. We want to be able to create a graph that would combine multiple metrics with different weights on the edges. And also, kind of one thing that we are exploring is Leiden should be good enough to run just in a single iteration. But this would require to kind of calibrate the weights of the graph that we're constructing, that we're passing to Leiden. And so this is single Leiden pass clustering, and also instead of running 200 times initial Leiden, we want to see, given the metrics for a city, if we can guess smaller range of Leiden resolutions that we want to consider and run in 10 instead of 200. Yeah, that's it. Development team. So main data scientist that kind of driving is Guido and his data science, and I'm helping him from engineering perspective. So if you have any questions. And the main point that I wanted to do with this presentation, that Leiden is very helpful for hex clustering. And I think for Uber, it's a new approach, and I don't think it's, I haven't seen any examples of this in the wild. So if you're working on your clustering, you can use this as well. Okay, so I think next one is Yining.
Welcome everyone, I'm Yining, and I will be presenting the delivery zone compaction and smoothing strategy today. First, let's have a quick look at our agenda. I will first start with a brief self-introduction, and then we'll discuss about the background and challenges we face, and we will dive deep into the isochrone multi-resolution, which is the strategy like we will focus on today, and also the compaction complexity. And we will wrap up with the summary and the key learnings and also the Q&A time. Okay, about me. So I'm Yingning. I'm a backend engineer at Uber. I'm from the merchant optimization team, where one of our core domains is optimizing merchant delivery zones. So our work is heavily used on H3. We use it to transform the real-world geography data into the backend data structure. Okay, background. So in the past, the Uber delivery zone is the radius-based delivery zone. It's just a circle. So on the right, you can see like this is a circle with a radius of 5.5 miles. So what's the problem with this approach? There are two major problems. The first is that this might include the hexagon like with long driving time. So for example, this one. Although the distance from the location, like merchant to this location is short, but its actual driving distance is very long. And also because this hexagon locates within the mountain region, so its actual like travel time is very long. The other problem is that the radius delivery zone might need hexagons with short driving time. So this location locates near to the highway. So although it is out of the delivery zone, its actual travel time is very short, but it was missed from this radius-based delivery zone. So what's the solution? The solution is isochrone. Yeah, I know some of you might be familiar with this, but to refresh your mind, like the definition of isochrone is a map online that connects all points that can be reached from a specific starting location within a set amount of time. So this can fit well in our delivery zone like use case. The starting location here is the merchant, and after we set like target ETA as the travel time threshold, we can draw a delivery zone. And also this can solve the problems I mentioned like in the last slides. Okay, so on the right, the green part is isochrone with 20-minute driving time. So you can see like it can indicate the real like road network, and also it's more precise. Also makes sense. However, this brings us new challenges. So if we use like low resolution, so the area of the hexagon is very large. So it might include some area that we don't want. What if we use a high resolution? Definitely it can give us very high accuracy. However, it's very expensive on the data storage. So this is a 30-minute isochrone. It has nearly like 600 hexagons. Unfortunately, Uber, the search engine, like has the limit on the data storage, so we cannot afford this expensive data storage. So what's the solution? That's why we have this isochrone multi-resolution strategy. So we can compact these 7 hexagons to a large one to save space. So it's 7 times cheaper. So we show this as an example. So for example, when the target ETA is 120 seconds, which means that we want to draw a delivery zone like within the 2 minutes. I know this is too small like in the real world, but this is just an example. So these 7 hexagons have the actual ETA from 80 seconds to 120 seconds. So all of them are below this target ETA, like 2 minutes. So which means that these hexagons are what we want. To save the space, we can compact them directly. But what if the target ETA is only 100 seconds? So should we compact? But if we compact, we will also include the hexagon F and G, right? So they are above the target ETA. So we don't want to include these 2 hexagons. So if we compact, we might include hexagons we don't want. But if we don't compact, we can drop F and G, but we will keep A to E. So we still need to store 5 hexagons. So data storage is a problem. So what we do here is that we need to trade off between the accuracy versus the data size. So accuracy here means that, so I assign each hexagon a score based on its ETA accuracy. So we use the target ETA minus the actual ETA. And the parent hexagon is the sum of the accuracy of its children hexagons. when accuracy is larger than 0, means that the hexagon's actual ETA is below the target ETA. So this hexagon is we want, so we call it accurate. When the accuracy is negative, it's the hexagon we don't want. And to trade off with the data size, to factor in the data size, we have a cardinality cost lambda. And this cost penalizes selecting too many hexagons and push the solution toward more compact representations. We can say the value of a hexagon is the accuracy of the hexagon minus the lambda. And we model this as an optimization problem. So we model the hexagon as trees. Each tree consists of a root H3 hexagon and all of its descendants across resolutions. The parent is the lowest resolution hexagon, like resolution 6 hexagon. The first layer is its children in resolution 7. The second layer is the children of, like in resolution 8. And in the final, we want to find the ancestor free to maximize the total value of the subset. The ancestor free means that if you select the parent, you should not select its children, which makes sense, right? If you compact to the resolution 6, so you don't need to select the resolution 7 hexagons. The full algorithm is that, so each leaf node, which is the highest resolution hexagon, gets a score based on target ETA minus actual ETA. And the internal node, which is the hexagon in the lower resolution, are defined as the sum of their children's score. And we subtract a constant cardinality cost from every node score, which penalizes selecting many cells. The intuition here is that choosing the parent hexagon is 7 times cheaper than choosing the children hexagons. However, doing so may include children we don't want. And then we solve a tree DP. And so for each node, either select the node itself or select the best selections from its children, whichever yields higher total score. Yeah, I know the algorithm is a bit like tedious and abstract, so I will walk through with an example. So we still use the example shown in the previous slides. When the target ETA is 100, and the lambda, the cardinality cost is 3. So we first need to calculate the accuracy for each hexagon, which is used at 100 minus their actual ETA. And when we calculate the value of the parent, we sum the accuracy of their children first, which is 20 plus 15 plus 10 plus 5 plus 5 minus 10 minus 20, which is 25. And when the lambda is 3, so we use the 25 minus 3 is 22. And regarding the children value, so first we don't need to include the children hexagon with a negative value. So we should only calculate the sum of from A to E. And the sum of the total value is the 40. So in this case, the children wins. So we should select from A to E instead of compact. And we favor the accuracy here over the compaction. What if the cardinality cost is 15? At this time, the parent value is 25 minus 15, which is 10. And this time, like only A has the positive value, so the value of the children is only 5. So at this time, we should return the compaction, which is the large hexagon. And in this time, we favor the compaction, we favor the size over the accuracy. So here's a good example, like you can see what the role the lambda is playing when do the trade-off between the accuracy versus the data size. Where the value is large, so we would do the compaction more. When the value is small, we will return more children hexagon. And the cardinality cost is a dynamic parameter. Due to the database limitation, we have a strict maximum limit on how many hexagons we can store per merchant. And we run a binary search to find the best cardinality cost to reach the target hexagon count. And the impact here is that, so here's the example, we reduce from 1,000 hexagons to only 100 hexagons. So it's around 90% save on data storage while still holding the 90% accuracy. We use the insect over union accuracy here. So it saves a lot on the data storage. Okay, this brings us to the compaction complexity. I think AJ just mentioned, talk about this a bit. So you can see here is a clearly like hole between the hexagons. I think this is a common pain point for the H3 in statistical, but this is not bug. So to explain this, like we need to explain the geometrically versus the logically. So geometrically, latitude, longitude is only covered if it sits physically inside the hexagon. And logically, after we compact a set of high-resolution cells, the new multi-resolution set logically represents the exact same original coverage. So this example, the black point, we can say that black point lies within the red hexagon, but not within the yellow hexagon geometrically. But since the yellow hexagon is the compacted representation of the red hexagons, the black point is logically within the yellow hexagon. So what's the impact on this? So in Uber Eats, we need to query, so the merchant delivery zone has a group of hexagons to represent the delivery zone. And we want to find if user's hexagon and the merchant hexagon has a match to know if the user is within the delivery zone of the merchant. But if we query if we query geometrically, so which means that we convert the user location to hexagon directly among resolution 6 to 8, we can say there's no collision here. So this would falsely tell the user is out of the delivery zone. So we should query logically. We first convert user location to the resolution 8, and then get parents of it into resolution 7 and 6. And in this case, we can see that the resolution 7 has matched with the merchant's hexagons group. And this is the full query logic. We first convert location to resolution 8 hexagon, and then get parents, and then to do the check. Okay. Yeah, before we wrap up to the Q&A, there are two major takeaways from the work of this strategy. The first is that there's no need to restrict ourselves to a single resolution. Yeah, I think it's pretty common that when dealing with the data, strict data storage or system constraints, I think this multi-resolution strategy is very effective. It can help us to reduce the data size significantly while still keeping a good accuracy. The second point is that compacting to a multi-resolution doesn't miss any coverage. It's lossless. The compacted multi-resolution hexagons represent the exact same coverage as its original high-resolution hexagons group. But you need to query this carefully. You should query this logically instead of geometrically. Yeah, at the end, I want to thank to the team. Yeah, I'm from the merchant optimization team, and also the engineers, Yang and Phil, who contribute a lot to this project. And also the AJ, before he left the Uber, he helped a lot to this project. So his left is a huge loss to the Uber and also to our team. Yeah, I think that's all. Any questions? Yeah, if you have a question, you can feel free to reach out me to offline. Thanks.
All right, that's all of our presentations for today. Thanks everybody so much for being here. I'm going to scroll us back to the welcome slide if you missed the link for the H3 Slack, or actually that's about to happen by somebody else. Thank you. Again, thanks to Uber for hosting us and for switching the slide back. And thanks to everybody here for attending. We'll be here for a few more minutes. I think we have the room for another 20, 30 minutes, something like that. So still time to get something to eat and say hi to people. Thanks so much.